Alright guys, so now we've got some idea of how to name some of the more common alkenes and alkanes. In class, we're going to cover how to name alcohols and haloalkanes. But for the sake of these videos moving forward, I'm just going to start to name them, and as you see them and get a bit more exposed to them, you'll see them in practice. So what we're going to start doing is going to teach you guys how to draw. You might want to get a piece of scrap paper so you can have a go at doing this, or you can doodle around the booklet to have a go. But it is important that you try these things, because just listening to me isn't going to help, I promise. So there are 3 different ways that we're going to learn how to display our molecular formulas. One is called displayed. So this is full displayed, and it looks like this, and it's called displayed because we can see every single bond and what it's bonded to. So when we have something like butanol, butan, 4 carbons, ol, OH, got an alcohol there. So when you got something like butanol, we can see all of the bonds in there. So carbon will always have 4 bonds, hydrogen will always have 1, oxygen will always have 2. So you can see oxygen's got its 2 there, and it just goes on like that. And I'll show you how to draw those later on. Condensed formula. This is the minimal amount of detail we can see. And the way that I teach you guys to do this is say it as you see it. And I'm going to show you guys that in practice a little bit later on. And then lastly, we've got our skeletal formula. Skeletal formula is the most common one. This is the one where you see me draw lines over everything. And then all we're doing here is we're simplifying the organic formula. So we're not having to write out C, 1,000 times and then 15 bazillion hydrogens. Instead, what we're going to do is, because we know it's an organic compound, we're just going to draw the lines. And every single one of these points of a line represents a carbon with saturated bonds. It's got the maximum amount of hydrogens in there. So you can see that. And then what we're doing is we just kind of emit that to save space. The only things that we'll draw on skeletal formula are the actual functional groups. So you can see here again for butanol, I've got 4 carbons, and I'll show you this in a bit more practice, but 1, 2, 3, 4, and that 4th one there represents this one, which is bonded to an OH, which you can see there like that. So those things are how they're mirrored. Let's take you through an example of how to do this. So here is a really simple breakdown of how it's done. On the left-hand side, what you can see is hexane, and on the right-hand side, you can see a much more complicated molecule that we don't need to know how to name, but I just wanted to show it you for practice sake. Let me go through the hexane example first, so you can see how we do this. We're going to start with a displayed structure. Hexane, we've got 6 carbons, and it's a doublet add 2 because it's CnH2n plus 2, so that is going to be H14. So now we need to arrange it so we have 6 carbons in a row, just like this. Every carbon needs 4 bonds, so we need to make sure that every single one of those has those bonds right there. Remember the ones in the middle over here like this, 1, 2, 3, and 4. You can see it's got bonded to 2 hydrogens up and down. So that still works. Now, for skeletal, what we're going to do is we're going to remove all those hydrogens. They're still there, but we're just going to hide them. And then we're going to draw it in a zigzag formation so we can actually count the carbons a little bit more clearly. So instead of drawing it in a straight line, we're just going to go up, down, up, down, up, down, up, down. Or down, up, down, up, down, up, down, up. And that's fine as well. Now instead, we're now going to get rid of every single carbon. So we're going to get rid of the C's, and every corner and edge becomes the carbon. So you can see here, this carbon is here, this one is here, this one is here, this one is here, this one is here, and this one is here. And then that is going to be our skeletal formula. Now, the way that I like to do this for hexane, so if I just wanted to draw hexane off the top of my head, I know I've got 6 carbons, and the way that I would do this is I would go, and you ready? 1, 2, 3, 4, 5, 6. It's important you start your first line with 1, 2, because remember, this is 1 carbon, and there's the second one. But you can see here, 1, 2, 3, 4, 5, 6, 6 carbons. So again, you're just going to go 1, 2, 3, 4, 5, 6. And that's the trick to doing that. You will get a lot more practice with this as you go along. But for now, what I'd like you to do is have a go at answering these questions here. Remember, for chloropropane, we've got a propane that's bonded to a chlorine. Just a Cl on its own, not a Cl2, just a Cl, like that. And I'd like you to draw the skeletal formula for that one. Okay, let's move on. Condensed formula. So this is one that we don't tend to see very often, but it can be really weird until you've used it a couple of times. And we're going to use something called the say it as you see it method. So I know you can see this in your booklets, but I'm going to hide it from you now. So I'm just going to hide this answer, and then we're going to go through it together to show you how I use this. Again, we're going to start with our displayed formula. You can see here I've started with pentane. It's got 5 carbons. Double it, add 2 is 12. That works out. On a displayed formula, pentane is a straight chain, ane, no double bonds, so it's just going to look like this. Now, to do a condensed formula, what we're going to do is we say it as we see it from the C. So C over here, what is that carbon bonded to? So I'm going to go C, got 3 hydrogens, 1, 2, 3. So it's CH3. That's bonded to a carbon, which is bonded to 2 hydrogens, CH2, which is bonded to another carbon, which is bonded to 2 hydrogens, CH2, which is bonded to another carbon, bonded to 2 hydrogens, CH2, and then it's bonded to another carbon, which is bonded to 3 hydrogens, which is CH3. And you'll see that when I remove this, it matches. It'll be CH3, CH2, 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 CH3. And that just gives us a really quick glance, and it just means that we can type it up, we can show it quite easily. We could also use brackets to shorten it. So you can see over here, if you're writing too many CH2s, instead of you going and writing this 5 times in a row, so you can see 1, 2, 3, 4, 5, you could put it in brackets and put a 5 down there to save you some time. Again, I really don't think we'll be doing many questions that ask us to do that, so I wouldn't worry too much, but I thought I'd put it there just in case. What I'd like to do now is I'd like to have a go at covering these questions over here. One thing I'd like you to note is during our condensed formula, if we have a double bond, we literally draw that as an equal sign or a double bond in that formula. Really straightforward. Have a go. So here you go. Lastly, the last way that we can draw these is by using a 3D representation, and we're going to call this wedge and dashes. We mentioned this really early on in the course, so if you still remember, really well done. But if you don't, here's a quick recap. So what we're going to have here is a molecule called methane. And if you remember with methane, methane's not flat, so these aren't right angles, that's not 90 degrees. Methane, we've got 4 bonding regions, so therefore we have a tetrahedral molecule. So it looks more like this. Not a C, there, H's. H, 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 and H. And these have a bond angle of 109.5 degrees, and it is tetrahedral. So that links back to your shapes from earlier on. Now, because it is tetrahedral, it means it works in 3D space, and we need to see which bonds are sticking out and which bonds are pointing in. The way that we do this is that we use a wedge to point towards us. So imagine this one is coming out of your phone if you're watching it on a phone. This one's sticking out of the phone and pointing toward you. And then what we're going to do is this one down here is pointing into your phone, so going through the back of your phone. And then the other 2 are sticking out at the top, and one's going to like the bottom left corner of your phone. So that shows it us in 3D. Now, for this, we just need to use a simple rule that works most of the time for you guys that I'm going to teach you. So, whenever we're looking at carbons, carbon will always have 4 bonds. When we're drawing each of those 4 bonds, one of them will be a dash, and one of them will be a wedge, and the other 2 will be lines. Let me show you this with ethane. So with ethane, we've got 2 carbons, no double bonds, it's ane, so I'm just going to go 1, 2. Ethane is C2H double it, add 2 is going to be 6. So I've got 6 hydrogens around this. Let me draw these in first, don't write this out because I'm going to change it. So I'm going to 1, 2, 3, 4, 5, 6. I'm going to draw those hydrogens in just like that. I'm rushing so I don't take too long. Now, like I said before, the rule of thumb is carbons will have 2 lines, 1 dash and 1 wedge. Now, I always find this easier to do the dashes and the wedges in the same plane. So I'm just going to do the top ones as wedges. So I've got 1 wedge, and the bottom one will be a dash. Carbon over here has 1 wedge and 1 dash. Now, truthfully, there is no difference where you put those wedges and dashes, so long as carbons have 1 wedge and 1 dash and bonded to them. It doesn't change the bonding, it just shows that in 3D, what are them sticking out, what are them sticking in. And that's it. What I'd like you to do is, I would like you to draw the 3D formula for the other 2 compounds. What I've done for you down here to save you some time is I've drawn you the displayed formula for pentane. So you can see it's 5 carbons. And what I'd like you to do is to add dashes and wedges to make it correct. Have a go at this, and let me know how you go.